So after that sort of fun interlude, let's go back for a moment to using torque to study rotation and rotational acceleration rather than the maybe more fun application of forces and torques to things that look like architectural structures. So let's use forces and torques to analyze the big red wheel that we first saw in the previous lecture. And let's say the wheel has rotational inertia I, and then let's say the string is wrapped around the wheel at radius r, and there's an object of mass m dangling on the string. For the dangling object, let's write Newton's second law, m a sub y equals the sum of vertical forces acting on this mass. And then for the cylinder, let's write the rotational inertia, which is some, we don't know the value, but let's say it's given to us, times the angular acceleration is the sum of the torques, and let's see what we get. So let's draw a free body diagram for this dangling mass, little m. So here it is, a conventional free body diagram. Let's let the y-axis point upward. So I think we're going to have a downward acceleration. So a sub y we expect to be smaller than 0. We expect a negative a sub y because the acceleration should be downward, and we're going to let the y-axis point upward. So we have an upward force, which is just the tension in the string, and we have a downward force, which is Earth's gravity, and it's also accelerating downward. So Newton's second law would give us m a sub y is up minus down. That's tension minus mg, which gives us tension equals m a sub y plus g, but a sub y is negative, so this is going to be smaller than mg. Now let's draw an extended free body diagram of the wheel to work out the angular acceleration of the wheel. And really, I think the only force that matters is the tension. There is a weight, but the axis of rotation is the axle through the middle of the wheel, so the weight of the wheel doesn't matter. It's going to have 0 lever arm. So I think the only torque that matters is the tension in the string times its lever arm. So writing the rotational inertia of the wheel times the angular acceleration of the wheel is the sum of torques on the wheel is pretty easy. And if we define the rotational acceleration to go clockwise, just because that's the way we drew the picture, then a positive tension should give us a positive torque, should give us a positive angular acceleration. So this is just this tension times the radius. So the only non-zero torque applied to this wheel, neglecting friction, is the string tension, and it has a lever, it's a vertical force, so it has a horizontal lever arm of r. Now, if these two masses out here were not oriented symmetrically, then they could exert a torque. So suppose one of them were in and one of them were out. Then if they were not oriented vertically, then there would be a non-zero torque. They would tend to pull one of them down to the bottom. But because they're oriented symmetrically, whatever torque one of them might exert is canceled out by whatever torque the other one might exert. So that's balanced. So there's really only one torque that interests us. It's the torque exerted by the tension in the string. So then we can plug in this expression for the tension, and we get that this is m times a sub y plus g times this lever arm r. Then, as long as the string is wrapped tightly around the wheel, then every time the string goes down by one circumference, the wheel will go around by one revolution. So we can write, just as we wrote, arc length is r times theta, and we wrote v equals omega r, we can write the magnitude of a sub y equals alpha r, except that we said that a sub y was negative. So if this wheel is accelerating clockwise, which would be positive alpha the way we've drawn it, then the mass is accelerating downward, so we need a minus sign. I think we have a sub y equals minus alpha r. That's because we have v sub y equals minus omega r. So if omega is clockwise, then if the wheel is going around at rotational velocity omega, then the mass is going downward with vertical speed omega r. But since we have our y-axis pointing upward, that would be v sub y equals minus omega r. So a sub y is the rate of change of v sub y, and alpha is the rate of change of omega. So a sub y is minus alpha r. Plugging that in, we get I wheel alpha wheel equals, so tension times r, m a sub y. Well, a sub y is minus alpha r, and then plus little g times big R. Now we have, and this is the alpha of the wheel. So we have two terms that have alpha, so let's put those together. Dropping the w subscript and just multiplying everything out on the right-hand side, we have I times alpha on the left side equals, so this term is a minus sign, minus m, and this other r gets distributed. So we have minus mr squared alpha, and then plus mgr. Then we can move this mr squared alpha term over to the left side to join the other term that has alpha. Now we have alpha isolated, so we can just divide both sides by I plus mr squared. So this is an exact expression for the angular acceleration of the wheel if the wheel has rotational inertia I, which includes the contribution from these big adjustable masses here, and if the thing on the end of the string has mass little m. And we said the first time we used the big red wheel that the tension in the string would just approximately equal mg as long as this acceleration stayed pretty small. And the tension in the string being approximately equal to mg is the same as the statement that this mr squared in the denominator is small compared to this rotational inertia. So if this mass is not too big, and in particular if this mass times this lever arm squared is very small compared to the rotational inertia of the big red wheel, then we just get the angular acceleration as mgr divided by I, which is sort of the approximation we were using in our mind's eye when we first saw the big red wheel and we were adjusting the radius and adjusting the mass and trying to see how the angular acceleration varied in the different circumstances. So it's often interesting in physics to evaluate limiting cases, and in the limiting case where the acceleration downward of this mass is much smaller than little g, then this expression would become just mgr divided by I. And the statement that the downward acceleration of this little block is much less than g is the same as the statement that this rotational inertia of the big wheel is much bigger than this little m times this r squared. So we can ask, why did increasing the dangling mass m increase the wheel's rotational acceleration alpha? Well, it's easy to see in this limiting case. If you increase m, then alpha gets directly bigger. If you don't use that limiting case, then you sort of have to argue that this I is much bigger than this term in the denominator. But as long as we don't make the mass here so big, or as long as we don't make the rotational inertia of the big wheel so small, then this mr squared term should be a lot smaller than this I term. So the angular acceleration alpha should just be pretty close to mgr over I. And then you can directly see that making this mass bigger increases the angular acceleration alpha. Why did increasing the radius r from which the dangling mass was suspended increase the wheel's rotational acceleration? Well, again, you can see this big r here upstairs. So in this limiting case where the rotational inertia of the wheel is much bigger than this mr squared, then you can see that if you make r bigger, then this angular acceleration alpha will be bigger. Why did sliding the big rotating masses farther out on the arms here decrease the wheel's rotational acceleration? Well, you can see if you make this I bigger, and it doesn't really matter in this case whether we have this other term here or not, making this I bigger certainly makes this angular acceleration alpha smaller. But really, when we were working with the big red wheel, we were using this limiting case where alpha is approximately equal to mgr over I. So making m bigger made alpha bigger, making r bigger made alpha bigger, and making I bigger made alpha smaller. So that all makes sense. But to get the answer in a really simple form, it helps to be able to use the approximation that the rotational inertia of this big wheel is much larger than this mass times this lever arm squared. Oh. That's really pretty slow. Let's go back now and use torque to analyze another problem that in chapter 11 we were only able to analyze using conservation of energy. So let's look at a cylinder rolling without slipping down an inclined plane. So let's see if we can directly calculate the acceleration now that we know how to use torque. So there should be three forces acting on the cylinder. What are they? Well, I think we have gravity acting downward, which I suppose will decompose. And we have the normal force acting perpendicular to the surface of the plane. And we have static friction. Static friction is what causes the cylinder to roll without slipping. And static friction is going to act tangent to the surface of the inclined plane. So let's draw a free body diagram for the cylinder, and then we'll draw an extended free body diagram for the cylinder. And then we'll figure out the torque created by those three forces. And then I think if we're talking about rolling without slipping, then we know how alpha and A are related. I think we'll find that A equals alpha R, just as we had V equals omega R. And then I guess we can write Newton's second law, F equals ma, and then we can write the rotational equivalent, tau equals I alpha. So let's get started. So here is the symbol representing the center of mass of our cylinder, and there's a downward force, the gravitational force by Earth on the cylinder, which just equals the weight of the cylinder. Then we have the normal force exerted by the plane on the cylinder. We don't know how big that is yet. And then we have the static friction force exerted by the plane on the cylinder. And we also don't know how big that is yet. So let's decompose gravity and figure out how big the downhill component of gravity is. So we'll cross off the gravity arrow. This angle is theta. This is mg cosine theta. This is mg sine theta. So we could draw the triangles, but this is sort of familiar. We know the downhill component of gravity is mg sine theta, and we know that perpendicular component of gravity that balances the normal force is mg cosine theta. So that's familiar from previous examples, so we won't take the time to draw the triangles this time. I guess we can see we made the friction arrow a little bit too long because the cylinder accelerates downhill, not uphill. So that seems like a more appropriate length because we know the acceleration is going to be this way, so it's going to accelerate downhill. And then we know it's not accelerating in the direction perpendicular to the surface. It's not accelerating this way. It is accelerating this way. It's not accelerating this way. So these two arrows have to balance one another. So that tells us that the normal force equals mg cosine theta. That's a consequence of the acceleration in this direction being 0. Then we know that the mass times the acceleration downhill, I'll just say this is downhill, is mg sine theta minus f static. So I think that's the information we can get out of the ordinary free body diagram. We get f normal equals mg cosine theta, and we get the mass times the downhill acceleration equals mg sine theta minus the static friction force. Now let's draw the extended free body diagram. I think we could do that just by annotating this circle. So here's the gravitational force, Here's the static friction force, and here's the normal force. A couple things to notice. This lever arm is R, and then if we choose the center of the cylinder as our pivot, the gravity force has 0 lever arm, and the normal force also has 0 lever arm because the normal force line of action passes directly through the center of the cylinder. You see, perpendicular to the surface of the cylinder here, and it just continues right up through the center of the cylinder. So this has 0 lever arm, and this also has 0 lever arm. So the only torque is the torque due to static friction. And that makes sense. The only thing causing this to rotate rather than just to slide down the hill is static friction. So using the center of the cylinder as our axis of rotation, we can write tau equals I alpha. So the only torque is this lever arm, which is the radius of the cylinder, times the static friction force. So radius times static friction equals I alpha. And then, because the wheel rolls without slipping, we know V equals omega R because we roll without slipping. So the rate of change of V is acceleration, and the rate of change of omega is alpha, and R is a constant. So the acceleration is just alpha times R. Or the angular acceleration, the rotational acceleration, is just the downhill acceleration divided by R. That's the more useful form. So the rotational acceleration equals the downhill acceleration divided by R. So I'll just write the downhill parallel part so it matches this. So combining this result with this result, we get R times F static is rotational inertia times downhill acceleration divided by the radius, which gives us F static equals downhill acceleration times rotational inertia divided by R squared. So now let's take this result and combine them, and I think that will tell us something useful about the acceleration. We'll plug in our expression for F static from down here. Next we want to isolate the acceleration so we can solve for it. So we can divide both sides by m. That gives us the downhill acceleration equals g sine theta minus I a downhill divided by mr squared. So this r squared became an mr squared. Then we take this term and move it over here. So see, we can just factor out the a downhill, and we have a downhill times 1, and we have a downhill times I over mr squared. So that gives you a downhill times 1 plus I over mr squared. That leaves just g sine theta on the right. So then we can divide both sides by this. We get a downhill. The downhill acceleration equals g sine theta divided by 1 plus I over mr squared. So this is that famous shape factor that we reasoned last week from conservation of energy considerations. So now we get it directly using torque. So the downhill acceleration, if there were no rotational inertia, it would just be g sine theta. That's a familiar result. And then for the hoop, if a hoop has just I equals mr squared, then the downhill acceleration is g sine theta over 2. So that's 1/2 the acceleration. Or if we have I equals 1/2 mr squared, then this is 1 plus 1/2 downstairs. So that's 3/2 downstairs, which would be like a factor of 2/3. So if we had a solid disk, then we would have 2/3 g sine theta for the acceleration. So this is a more direct argument showing you that the downhill acceleration is smaller for the object that has the larger rotational inertia for a given mass and a given radius. So the rotational inertia divided by mr squared is something you might call the shape factor, or sometimes this whole denominator is called the shape factor. So I copied that result down here, and you can compare it with what I worked out earlier on the slide, and you can see the same result from the slide. While we're here, let's revisit something that we didn't explain a few weeks ago when we used the center of mass chalkline to suspend an object from several different points, and we used a plumb bob on the end of a chalked piece of string to find the center of mass of various objects. At that time, you had to take it for granted that somehow the center of mass would be directly below the pivot point. But now we can explain using torque why that happens. You know that if an object has a symmetry axis, then the center of mass must lie along that symmetry axis, but not all objects have symmetry axes. So here's a trick. If I hang this object suspend it from one point, just as if I take this plumb bob and suspend it from a point, that the center of mass of this suspended object will stay directly below the point of suspension. Now you know where the center of mass of this object is because it's highly symmetric. Somehow the center of mass of this object must be somewhere directly beneath this point at which we're suspending it. Let's narrow down where that center of mass is by using a chalk line. So when I was a kid, my dad was a carpenter. In the old days, people would measure out straight lines by snapping a chalk line. We have kind of an artificial chalk line here. I'm going to rub red chalk on this piece of string, and it's going to be our ad hoc chalk line. So I'll pull this taut and I'll snap it. So there's an old carpenter's trick. So you say, okay, the center of mass must lie somewhere along that chalk line. Why does that make sense? Because you know the center of mass must be below the point at which this object is suspended. Then suspend it from a different point, and then we'll take our chalk line again. Seems like the center of mass must be somewhere below there. I will pull it taut and snap it. And okay, it seems plausible the center of mass is there, but let's do one more. Let's suspend it from here. The object is just hanging from this point, and the plumb bob is hanging below this point. I'll just pull everything taut and snap the chalk line. And it seems like a pretty good confirmation. We have 1 line, 2 lines, 3 lines, and they all more or less intersect here. There's maybe like a ½ centimeter offset. But now, let's take a less symmetric object like this. You say, well, where is the center of mass of this thing? You say, well, the center of mass of this thing, probably somewhere around here, but we don't really know for sure because it has an irregular shape. Let's try the same trick. Now that we have proven with an object of pretty simple shape that this trick seems to work, let's try repeating the trick with this not very symmetric object. If we first suspend this object from this point, say, okay, seems like the center of mass must be somewhere below there. Pull everything taut and snap, and I have a nice red line there. And then let's try a different suspension point. So let's suspend it from this point. Okay, so it seems like the center of mass should be somewhere below that. So the plumb bob's hanging down, so we think the center of mass should be somewhere along where that line is now. So let me just pull it taut and then snap it. Okay, so we have a candidate here, but let's do one more line to get a cross check. What if we suspend it from this point? Okay, so we'll make it taut and snap the chalk line. And that seems, okay, again, there's maybe like ½ centimeter or so imprecision in our method, but it seems like the lines all come together somewhere around here. And in fact, if we take this funny shaped object and if we suspend it from right where the lines seem to cross, it no longer has any preferred direction to orient itself because the point of suspension is right at its center of mass. Okay, so that's an irregularly shaped object. Now, at the time we're filming this, the Summer Olympics just finished, and one really impressive event is the pole vault. You wonder, how do you get your center of mass way up over that pole? Well, it turns out you may not actually have to get your center of mass all the way over the pole to get your body over the pole. So let's see where this pole vaulter's center of mass is when they're oriented in a shape like this. Let's start with this. So it makes sense, like maybe the center of mass is somewhere in the middle of the body, so it seems like the center of mass of this person is somewhere beneath this point of suspension. So let's try our usual trick with the chalk line. You say, okay, the center of mass should be somewhere below there, and snap the chalk line. Okay, then let's try a different point of suspension. What if the point of suspension is something like this? Oh, gee, something surprising seems to be happening. Seems like the center of mass must be somewhere beneath this point. Let's keep going. Okay, let's suspend our pole vaulter like this. And you say, okay, the center of mass of this shape must be somewhere along this line. I have here a clipboard, and it has a clip on one end, which is why the center of mass is a little bit toward this side from the actual center. So then notice that if I hold it here, the center is directly below. If I hold it here, the center is directly below. If I hold it over here, the center is directly below. If I hold it up here, the center is directly below. So it seems as if no matter where I decide to grab this clipboard, the center of mass appears directly below the pivot point, as long as I pinch gently with my fingers so that the clipboard is able to rotate to orient itself so that the center of mass goes directly below. So now that we know about torque, now we know that the line of action of gravity acting on an object passes through that object's center of mass. If I create a pivot with my fingers, then the lever arm between the line of action of gravity and the pivot creates a non-zero torque. Once the center of mass is directly below the pivot, now the line of action of gravity passes directly through the pivot and the torque is zero. So here I'm pinching. If the center of mass is not directly below the pivot, then gravity will exert a non-zero torque. That torque only becomes zero once the line of action of gravity passes directly through the pivot. The line of action of gravity passes directly through the pivot if the center of mass is directly below the pivot. Again, if I suspend this object from this pivot P, here's its center of mass. The line of action of gravity points straight down and passes through the center of mass of the object. So you can see that there is a non-zero horizontal lever arm going with this vertical force, so there will be a counterclockwise torque in this case. So as drawn here, this object is not in equilibrium. In this case, by contrast, the pivot is up here, the center of mass is directly below the pivot, and you can see that the line of action of gravity, which points directly down from the center of mass, passes directly through the pivot. So there's zero torque here because there's zero horizontal lever arm to go with this vertical force. On the one hand, you could argue that we are explaining the obvious. Of course, the center of mass winds up below the pivot. On the other hand, you say, well, how do I relate my intuitive knowledge that the center of mass should wind up below the pivot with my knowledge of physics? So now that we have an understanding of torque, we can see that if the center of mass is directly below the pivot, then there is no torque trying to change the orientation of this object. Whereas if the center of mass is not directly below the pivot, then in this case there's a counterclockwise torque trying to reorient this object so that the center of mass is indeed below the pivot. Here is a classic equilibrium problem. Here in orange is our ladder. The top end of a ladder of mass m rests against a smooth wall. What does smooth mean? Smooth is sort of a code word here for slippery, meaning no friction. So there's no friction between the wall and the ladder, but there will indeed be friction between the floor and the ladder. The top end of a ladder of mass m rests against a smooth wall, and the bottom end rests on the ground. The coefficient of static friction between the ground and the ladder is mu static. What is the minimum angle between the ground and the ladder such that the ladder does not not slip. Oh, so let's start by drawing an extended free body diagram for the ladder. So here's the ladder, here's the floor, here's the wall, here's the angle theta between the floor and the ladder. And it seems like we're going to argue that if somebody put the ladder like this, then it would slip. If the ladder is up really close to vertically like this, then it will not slip, but of course you have a different danger. If you climb up the ladder, then it might tip over. So it seems as if the closer to horizontal you put the ladder, the more risk that the ladder will slip out from under you. So you want the ladder to be closer to vertical so that it's less likely to slip. Of course, if you're accustomed to climbing ladders, you know that if it's too close to vertical, then it becomes unstable and can fall backward. Let's draw the forces acting on the ladder. The wall exerts a force to the left on the ladder. So we're going to call this the contact force. That's actually kind of a normal force. Let's call it the normal force by the wall on the ladder. But then let's give it a nickname. We'll just call it the wall force. It's only perpendicular, normal to the wall, because we somehow claim, and we'll see why in a moment, that there's no friction between the wall and the ladder, or there's only negligible friction between the wall and the ladder. So there's no tangential contact force here, which would be friction. Instead, there's only a normal contact force here between the wall and the ladder. When we draw things, once we start to analyze things that look more like architectural structures, the way we will indicate that this force can only be normal and not tangential is to put a roller skate here. So it will be a roller support. So it will look like a little roller skate between the ladder and the wall, which makes it visually clear that there is no tangential force. There's only a perpendicular force, only a normal force exerted by the wall on the ladder. So we might do that in the future, but for the moment, we'll just make it explicit by drawing only a normal force. We will not draw a friction force. At the lower corner of the ladder, however, we have both a normal force and a friction force. So let's draw them both. So here is F normal by the floor on the ladder. So I'll give that a nickname. I'll just call it F normal. And then here in this direction is the static friction force between the floor and the ladder, and I'll give it a nickname. I'll just call it F static. We need one more force, which is the weight of the ladder. So we'll draw that at the center of mass of the ladder. So this is the gravitational force by the earth on the ladder, and we'll just call that mg. Now we can compare with my pre-drawn diagram. So my diagram has F normal acting upward at this lower corner. So we have F normal acting upward. We have F static acting to the right. Here's F static acting to the right. We have mg acting downward from the center of the ladder, and we also have mg here acting downward from the center of the ladder. And then here is F wall acting to the left at the top of the ladder. So here's F wall acting to the left at the top of the ladder. And we note that the wall is slippery. Now you might ask, why do we have to say that the wall is slippery? Well, if you count the number of unknowns, the weight of the ladder is a given, so it's known. This force exerted by the wall is unknown. This normal force exerted by the floor is unknown. And the force of static friction is unknown. Unlike kinetic friction, which we know once we work out the normal force, static friction is a force whose magnitude we don't know until we work out how big static friction needs to be to keep the object from slipping. So we have three unknowns: F wall, F static, and F normal. Now if the wall were not slippery, we would have a fourth unknown force, which would be the static friction force exerted by the wall on the ladder. And we know that when doing statics problems in a plane, we only get three equations, so we can only solve for three unknowns. So if we allowed for friction at the wall, we would not be able to solve the problem using statics. A problem that you cannot solve using statics is called a statically indeterminate problem. It actually is possible to solve problems that have more unknowns than you're able to determine using statics, but to solve them you need to include additional information about the elastic properties of each object in the problem, so you see how the various objects deform in response to the forces applied on them. We don't know how to do that yet, so we're going to solve only statically determinate problems. Is the slippery wall more like a pin or roller support? So we haven't really talked about that in detail yet. We will soon. But if you remember from the arch problem, the hinge at the top of the arch was a pin or a hinge. It could exert forces in two different directions, whereas the skateboards underneath the arch could exert only forces normal to the surface on which the skateboards roll. In other words, only forces normal to the floor. So the slippery wall is actually just like a roller support. So if Professor Farley were going to draw this ladder problem, he would probably draw a little roller skate here. Not a roller skate on the ground the way you would normally see a roller skate, but a roller skate up against the wall. And you'll see us do something very similar to that in the future. What plays the role here that string tension played in the arch problem? Well, I would say static friction plays the horizontal buttressing role that the string tension played in our arch problem. Does the combination of two forces at the bottom act more like a pin or a roller support? Well, so this combination of a vertical force and a horizontal force, both of which have magnitudes that we need to determine by solving the problem, is actually exactly like a so-called pin support or a hinge. It's like the hinge that we had at the top of the arch in the previous problem. That probably seems a little mysterious at this stage, but it will become more clear as we work more examples, and especially as we see more examples that look architectural. Which forces would an engineer call reaction forces? You'll also see more of this once we start reading and looking at examples that look more as if they're drawn from architecture. But it is my impression, I've never actually had an engineer confirm this to me or argue with me about it, but it is my impression that when one draws forces in structures problems, the forces whose magnitudes are given, like the weight of something, are called loads. And then the support forces whose magnitudes have to be determined by solving the problem. And the normal force is an example of that kind of force. you don't know how big the normal force is until you solve the problem to see how big the normal force has to be. The normal force is a force whose magnitude will take on whatever value it needs to be to keep the object in equilibrium. So that's an example of a reaction force. And static friction is an example of a force that will take on a value as big as it needs to be, up to a limit, to keep the object in equilibrium. So I claim that the static friction force and the normal force and this other normal force exerted by the wall are all examples of what engineers would call reaction forces. They are forces that you know are there, but whose magnitudes are not given a priori. They are forces whose magnitudes take on whatever value is needed to keep the object in equilibrium. And then if that value that you determine to keep the object in equilibrium is bigger than some maximum allowed value, you say the structure as drawn fails, or somehow the support that you've drawn is inadequate for the job you need it to do. So again, I say the weight of the ladder is a load, it's a given force, and this normal force, and this static friction force are all what engineers would call reaction forces. If you look really closely at slide 52, you'll see that I drew a little roller skate up here between the wall and the ladder as an example of what a roller support looks like. So what choice of pivot axis will give us the simplest torque equation? So I kind of wrote this in engineer terms. The sum of moments about the z-axis is 0. In any case, the torque or moment equation can be made as simple as possible. In other words, an equation involving only two variables. You know that the algebra is simpler if each equation that you write down contains the smallest number of variables. So if we choose an axis judiciously, we will get an equation, a torque equation, also known as a moment equation, that involves only two forces. How can we do that? Well, we have four forces. 1, 2, 3, 4. It seems like if we put the pivot here, we would have three forces. Here we would have three forces. But if we put the pivot here, then any force whose line of action passes through that pivot has 0 lever arm, therefore it does not appear in the equation we write down. So I think the bottom of the ladder is the most convenient choice of pivot for this problem, because then the torque equation will directly relate gravity and the normal force exerted by the wall and nothing else. So that'll be a pretty simple equation to work with. In fact, it will then involve only one unknown. It'll involve two forces, one given and one unknown. So if we write down a torque equation using the bottom of the ladder as pivot, we can directly solve for this force exerted by the wall in terms of gravity and this angle theta, which will probably make the rest of our job easier. So I think if we use the bottom of the ladder as the pivot axis, that will simplify our torque equation, also known as our moment equation, because the equation we write down will involve one given force and one unknown force. So it will let us immediately solve for that one unknown force without any other equations yet. Let's let L be the length of the ladder. How do I write down the torque equation about the bottom end of the ladder? So our convention is counterclockwise minus clockwise. So you can look at these possibilities, but let's just try to write it down. 0 equals the sum of torques counterclockwise about P. So I decided to label this bottom point P. You don't have to label it, but you could say about the bottom of the ladder, but let's just call that point P. So let's look for counterclockwise torque. It seems as if the normal force exerted by the wall on the ladder will give us a counterclockwise rotation with respect to this pivot. So this is F wall, and then what perpendicular distance do we multiply by? So that is a horizontal force, so we want a vertical distance. From the pivot to the line of action, here's the line of action of that force exerted by the wall. The vertical distance to go with our horizontal force is the length of the ladder times sine theta. That's our counterclockwise torque. Then the only other torque we have is the torque due to gravity, which is clockwise, so it gets a minus sign. The force magnitude is mg. That's a vertical force, so we want the horizontal distance between the line of action of that force and the pivot. So that would seem to be 1/2 L cosine theta. L cosine theta is the distance from here to the wall, so this must be halfway. Once again, if the length of the ladder is L, then this vertical dimension must be L sine theta, and this horizontal dimension must be L cosine theta if we're measuring theta from the horizontal up to the ladder. So which one of these results looks like our equation? F wall L sine theta minus mgl over 2 cosine theta equals 0. I think I like H, hotel. Answer H. F wall L sine theta minus mgl over 2 cosine theta equals 0. We can then directly solve that equation for F wall. The L cancels out, so we can put F wall on the left and this other term on the right. F wall sine theta equals mg over 2 cosine theta. That gives us F wall equals mg cosine theta over 2 sine theta. So it seems like F wall is mg over 2 tan theta. The next thing to ask is, what do we learn by making the forces acting in the x direction add up to 0? And then what do we learn by making the forces acting in the y direction add up to 0? Let's start with the x forces. So 0 equals the sum of forces in the x direction. So we'll do right minus left. That seems like F static to the right minus F wall to the left. That tells us that F static equals F wall. So F static also equals mg over 2 tan theta. Okay, so F static equals equals F wall, which equals mg over 2 tan theta. Next, we can ask, what does the sum of forces in y give us? 0 equals the sum of the forces in the y direction acting on the ladder. Let's do up minus down. We have F normal upward and gravity downward. So F normal equals mg. It seems like what we learn from the sum of forces in x equals 0 is that F static equals F wall. And what we learn from the sum of forces in y equals 0 is that F normal equals mg. Now let's go back to the original question. What is the minimum angle between the ground and the ladder such that the ladder does not slip? Well, to know that, we have to work out the static friction force and compare it with the maximum allowed value for the static friction force. The ladder will slip when static friction gives out. Static friction will give out and let go when the required force of static friction is larger than mu static times F normal. So let's figure out where that happens. Static friction will let go when the required static friction force is bigger than or equal to mu static times F normal. So let's figure out when that happens. So we want mu static F normal equals F static is just when that barely happens. So that's mu static mg equals mg over 2 tan theta. The mg cancels. So the ladder slips if F static is bigger than mu static F normal. So the ladder slips if this 1 over 2 tan theta is bigger than mu static. So the ladder slips if tan theta is smaller than 1 over 2 mu static. So the ladder does not slip if tan theta is bigger than 1 over 2 mu static. So the minimum angle, if the ladder is to stay up there without slipping, is arctan of 1 over 2 mu static. So we need theta to be bigger than arctan of 1 over 2 mu static. And I think we have a demonstration that shows you that if theta gets too small, in other words, if the ladder gets too close to horizontal, then the ladder does indeed slip. Here's my model of the ladder. This is the wall. This ping pong table surface is the floor. And I'm trying to control the surfaces a little bit. So I'm hoping I made the friction pretty low up here, and then we should be able to see that if it's close to vertical, it's not going to slip. I mean, it might tip over, but it's not going to slip. And then we can see how far away from vertical, how close to horizontal do we have to make it before it slips. Okay, it seems to slip there. So if I put it like this, it slips right away. If I put it like that, it doesn't quite slip. But if I go out just a little bit, it slips. Now let me try what I think is probably a slipperier surface. Oh, look at that. See, on this surface, even when it's pretty close to vertical, okay, now I guess up here, seems okay. Oh, even there, oh, that's pretty good. That's a very slippery surface. So on this surface, it seems like if it's very close to vertical, it doesn't slip, but I don't have to get it very far from vertical. Before it starts to slip. Ah, okay. And I think the wood surface of this clipboard may be somewhere in between. Let's see. Maybe it's about the same as a ping pong table. Here's a metal clipboard. I feel you can never have too many clipboards or too many different kinds of clipboards. This should be reasonably slippery. Gee, it's actually not very slippery. Oh. Well, that's pretty good. Much to my surprise, it does not slip very easily on this surface. Now I have an option to take the tape off the bottom of this ruler, so then it's metal on metal. Oh, I think that slips more easily. Meanwhile, let's add a little embellishment. Suppose we add to this picture a person of mass m who has climbed up a distance d from the bottom along the length of the ladder. Let's see if that changes where the ladder slips. Maybe we'll see that the higher up she climbs, the more likely the ladder is to slip out. So let's update our extended free body diagram and see how to write the torque equation for this case. So here is a person who has climbed up a distance d from the bottom of the ladder, and so then her weight is now also borne by the ladder. So this will be, I'll call this big mg. So we'll have big M is the mass of the person, and little m is the mass of the ladder. Now let's write the torque equation. 0 is the sum counterclockwise about pivot p of torques, which you could also say is moments about the z-axis. You see, if this is the x-axis to the right and this is the y-axis upward, then the z-axis would point out of the plane of the page. Out of the plane of the page to me appears to be toward me, but actually the way you're looking at the board is actually toward you. So the z-axis is toward you if this is x to the right and if y is up. We want counterclockwise minus clockwise. Counterclockwise we have F wall times the length of the ladder times sine theta. That's the only counterclockwise torque. Then clockwise, we have the weight of the ladder. So the force exerted by the wall on the ladder was horizontal, so we wanted the vertical distance from the pivot. The weight of the ladder is a vertical force. We want the horizontal distance from the pivot to the line of action of the weight of the ladder. So if we extend this down to here, we want, as we did a moment ago, L over 2 cosine theta. Now we have one additional torque due to the weight of the person. If we extend her weight line of action down to the axis, we can see that the horizontal distance to go with this vertical force is d cosine theta. Let's see which one of these seems to agree with this. FWL sine theta minus mg L over 2 cosine theta. So F wall L sine theta minus mg L over 2 cosine theta. They all seem to start that way. And then we want minus big mg d cosine theta. Minus big mg d cosine theta. So I think I like G, golf. Minus big mg d cosine theta. I think that makes sense because the vertical force was big M times G, and then the horizontal distance to go with that vertical force was d cosine theta, where d is how far up the ladder she has climbed diagonally. We can then solve this for the force exerted by the wall. This time the L doesn't cancel out. I guess if we want to make it look neater, we could put L tan theta in the denominator. In fact, we could even divide everything by big L. That's good because then we can get the fraction d over L she climbed up the ladder. So there are always many choices you can make when trying to clean up an expression like this. I decided to divide everything by L, and I decided to multiply everything through by 2. So then the denominator has a 2, and this term has a 2. The 2 went away here just because it seems nicer to have a 2 instead of a 1/2. And then I said sine over cosine is tan theta. And then you can see that the result seems to depend on this value d over L, which is what fraction of the ladder she's climbed up. So now let's see what we learned by summing the forces to 0 in the x direction and summing the forces to 0 in the y direction. And then finally we can ask, for a given angle theta, how far up can she climb before the ladder slips? If we sum the forces in x to 0, we get, let's do right minus left, F static minus F wall equals 0. So again, we get F static equals F wall. If we sum the forces in y to 0, let's do up minus down. So we get F normal minus the sum of the two weights. So F normal is just the sum of the ladder's weight and the person's weight. Now let's do as we did before and figure out when the ladder slips. So that basically happens when F static equals mu static times F normal. So let's work out how we get F static to equal mu static times F normal. So you know the ladder will slip if F static that we require is bigger than or equal to mu static F normal. So F static is m little mg plus 2 big mg d over L divided by 2 tan theta. And if that is bigger than or equal to mu static times the sum of the two weights, then the ladder will slip. So we want to know how far up the ladder she can climb before the ladder starts to slip. So I guess we really want d, or d over L. So let's try to isolate that. So we can move mg over to the right hand side, and then next we can divide by everything we don't want here. So let's divide by 2 big mg. And then we can also cancel the little g from top and bottom. I'm not sure that this answer is all that illuminating. It's kind of more interesting to look at this expression. And let's remember again that the ladder slips if the required F static is bigger than this. So the ladder slips if this left side is bigger than the right side. And you can see that as she goes up higher and higher up the ladder, this d over L gets bigger. So d over L is 1 if she's all the way at the top. D over L is 0 if she's at the bottom. So you can see the higher up she goes, the bigger the left side gets, so the easier it is to slip. So it does seem like the higher up you climb on the ladder, the bigger the risk of slipping. And I guess another interesting question would be that you could evaluate is, what angle do you have to put the ladder at so that even if you're standing at the very top of the ladder, you are not going to slip? That might be a good homework problem too. You want to hang a sign of mass little m that advertises your new business. To do this, you attach a beam of mass capital M and length L to a wall at its base by a pivot P. You then attach a thin cable to the beam and to the wall in such a way that the cable and beam are perpendicular to each other. The beam makes an angle theta with the vertical. You hang the sign from the end of the beam to which the cable is attached. A, what must be the minimum tensile strength of the cable? That's really asking what's the largest possible value for the tension. And there's only one possible value in this problem for the tension, so it's really just asking what is the tension. B, determine the horizontal and vertical components of the force the pivot exerts on the beam. Okay, so we basically want to determine three unknowns, the tension and the x and y components of the force exerted by the pivot on the beam. So I think, as usual, we should start by drawing an extended free body diagram for the beam. The first question is, what forces act on the beam? So you should think for a minute and see, you might even want to pause and see if you can come up with your own answer. I think when we draw the extended free body diagram for the beam, The first thing we're going to find is the weight of the beam itself. So I think that will be a force big mg pointing straight down from the center of mass of the beam itself. Then there is a downward force acting on the beam due to the small cable that suspends the little sign that's advertising your business. So that is little mg. This first one was big mg if big M is the mass of the beam, and this is little mg if little m is the mass of the sign. Then there's the cable tension. So there's a contact force by the cable on the beam, which points along the axis of the cable. So you could just call that T, tension T. And then at this pivot, there is a horizontal component and there is a vertical component of the force exerted by the pivot on the beam. So I already started an extended free body diagram, so let's compare notes. I just called this force T, since it's the tension. Then I call this force big mg, where big M is the mass of the beam itself, and its line of action passes through the center of mass of the beam. And then I call this force little mg, so little m would be the mass of the sign that we are suspending. And then, oh, by the way, notice that this is drawn as a right angle. And then we have two components, the horizontal component and the vertical component of the force exerted by the pivot. We might as well label the pivot P. And then this is an angle theta from the vertical down to the axis of the beam. And then I think this must also be that same angle theta from the axis of the beam to the vertical gravity line. And therefore this must also be that same angle theta. One thing that's tricky is in this problem, theta is measured with respect to the vertical. So when we use our trigonometry functions, horizontal distances will have a sine theta in them, and vertical distances will have a cosine theta in them because we're measuring theta with respect to vertical rather than with respect to horizontal. So as usual, we can write three equations for the beam, and it's a good thing then that we have just three unknowns. So we have to say that the forces in x add up to 0, the forces in y add up to 0, and the torques add up to 0. We need to choose some pivot point for our torques. It seems as if we are provided with a natural pivot, and one advantage of using this pivot P as the pivot point for our torque calculations, you're allowed to choose what you use. Even if there is a natural pivot in the problem, you're still allowed to choose a pivot in these equilibrium problems. The nice thing about using point P as our pivot is when we write the torque equation, Fpx and Fpy will have 0 lever arm. So we will directly get an equation that relates this tension T to this weight big mg and this weight little mg. So that actually seems quite nice. So let's start by writing down the torque equation, pivoting about point P. So we'll do counterclockwise minus clockwise about point P. The only force here that will give us a counterclockwise torque is the tension. Oh, now this is tricky. So it's neither horizontal nor vertical. It's at some funny angle. But we know that the angle for this tension force is perpendicular to the beam axis. So therefore, the correct lever arm is the entire length of the beam. So this length L, this displacement L, is perpendicular to this tension whose force points along the axis of the cable. So it's just T times L. Then we have two clockwise torques. They get minus signs. We have little mg for the sine over here. So that's times L sine theta. We want the horizontal distance. We want to take the entire length of the beam and pick out the horizontal part to go with the vertical force. So because we're measuring angles with respect to the vertical, this horizontal part will be L sine theta. And one way to see that, if you drew this triangle, then the length that we are looking for, which is really down here, but we can put a copy of it up here. So this length that we are looking for divided by L is opposite over hypotenuse, which is sine theta. So that makes sense. Then we have big mg, the weight of the beam itself, and its lever arm is half the lever arm of the sine. So it's also a vertical force, but it's halfway up the length of the beam. So that's L over 2 times sine theta. So this is nice. The L's will cancel. This gives us directly an expression for the tension. All of this adds up to 0. So we can leave the tension on the left side and move these other terms over to the right side. We get the tension equals little m plus big M over 2 g sine theta. Now we can write that the sum of forces in the x direction acting on the beam is 0. If we want to do right minus left, it might be helpful to decompose the tension. I think if we draw a horizontal line, which I've drawn in purple, up where the cable meets the wall, this angle, I claim this angle is theta. And one way to see that is this is theta. So this angle must be 90 degrees minus theta. And then this angle must be 90 degrees minus 90 degrees minus theta, which is theta. Another way to see that is theta is the beam's angle with respect to the vertical. And we know the cable is perpendicular to the beam. So if this is the beam's angle with respect to the vertical, then this must be the cable's angle with respect to the horizontal. You can also see that if we made this angle theta very small, then we would make the cable almost horizontal. So that also seems to make sense. So I claim that this angle of the cable down from the horizontal is the same theta. Therefore, this angle on this diagram is theta. So the tension is an angle theta from the horizontal. So the horizontal component would be T cosine theta, and the vertical component would be T sine theta. So it seems as if the horizontal force to the right, well, we've assumed it's to the right. If it's to the left, we'll get a negative answer. The horizontal force to the right exerted by the pivot on the beam minus the horizontal component of tension, which we've drawn to the left. Those two things must sum to 0, which tells us that this horizontal force force exerted by the pivot on the beam just equals t cosine theta. Then we want the vertical forces on the beam to sum to 0. So we have up minus down. Here's the vertical force exerted by the pivot on the beam. And we also have the vertical component of this tension plus t sine theta. And then we have the two weights. That gives us Fpy equals the sum of the two weights minus the vertical component of this tension. So assuming that we have solved this correctly, and I did not write down a correct answer anywhere, so I can't say for certain, I can't check it against work that I did last year, it seems as if the tension is little m plus a half big M together times g sine theta. And then it seems as if the vertical force exerted by the hinge is the sum of the two weights minus t sine theta, where you would have to plug in this value of the tension. And then it seems as if the horizontal force exerted by the hinge is t cosine theta, where again you'd have to plug in this expression for the tension. Here's a problem involving a cable, which is going to be an interesting segue toward our studying trusses soon. A tightly stretched high wire, that's like a wire that a kind of daredevil stunt person will walk on. A tightly stretched high wire has length L equals 50 meters. It sags by D equals 1 meter when a tightrope walker of mass M equals 51 kilograms stands at the center of the wire. What is the tension in the wire? That means the tension when the tightrope walker is standing on it. I think we have a picture that looks something like this. Here is the unstretched length in blue, 50 meters. After the person stands in the middle, we have the person's weight, mg, applied at the middle. And then, so it sags by a distance, little d, which we are told is 1 meter. So from here down to the place where the person's weight is applied after it is stretched is 1 meter. So this little distance is d. So we have a force downward here, mg. And then the tension is T over here, and the tension is also T over here. The tension in the wire is T. So I think we want to know how big is the tension to support this. So the situation is symmetric because the person is in the middle. So this angle theta is the same as this angle theta. And the tangent of this angle theta must be d over a half L. So I claim that opposite over adjacent, which is a tangent, must be this little d divided by half of this big L, because adjacent here is 1/2 L, and opposite here is d. Then I claim that to solve this problem, we want to write the equilibrium equations. Well, actually, all we really have are forces. We want to write the two force equations for this point. Maybe I'll call it the point P. For the point P where the person is standing. Let's try that. So at point P, let's say point P is in equilibrium. It's like that little spot on the cable. So the sum of forces in Y, up minus down, is we have t times sine theta on the left, and we also have t times sine theta on the right. So I think we have 2t sine theta up, and then downward we have mg. So those somehow should sum to 0. Actually, I think that might be everything we need. See, if you wanted to, you could say 0 is the sum of the forces in x, but that would just be t cosine theta minus t cosine theta, which is 0 anyway, so that doesn't tell you anything. So there's really only one equation of interest, and it tells us that 2t sine theta equals mg, therefore t equals mg divided by 2 sine theta. Oh, and what is sine theta? Well, actually, sine theta is d over the square root of L over 2 squared plus d squared. And actually, for an angle this small, sine theta and tan theta are not very different. We can work it out exactly. I claim that sine theta and tan theta are very similar. So tan theta is 2 over 50, which is 1 over 25, which is 0.04. Let's see what sine theta is. Plugging in numbers, well, we got tan theta is 0.04, and sine theta is 0.03997, which is not very different from 0.04. So really, sine theta and tan theta are pretty similar. That's saying that square root of L over 2 squared plus d squared is not very different from just plain old L over 2. So in this case, d is so small compared to L that this expression is almost exactly the same as 2d over L. So if you really want to be exact, you get an expression something like this, but this is almost exactly the same as mg L over 4d, because we have mg over 2 sine theta, and sine theta is very close to 2d over L. So there's 2 times 2d, and then you put the L upstairs. You can show that to yourself by plugging in numbers if you like. So what we get for the tension, if we put in numbers, is 6,250 newtons. What's kind of remarkable about this is the tension in the wire is much, much bigger than the weight of the person. See, the weight of the person is about 500 newtons, but the tension in the string is about 6,000 newtons. So the tension in the string here is more than 10 times as big as the person's weight. And that's because it has the sign of this small angle in the denominator. I am told that this is potentially a useful trick if your car is ever stuck in the snow. If your car is stuck in the snow, the tempting thing to do is to take a rope and pull this way. And I once got some really big, strong friends to do that, and they did get my car unstuck. But I am told, I've never tried this, I've been looking for an excuse to try this, that a better technique is to take the rope and tie it either to a tree or to a pickup truck or to some strong object, and then push perpendicular to the rope. See, so if you push the rope, if you push on the rope, I mean really you push horizontally, but I don't have any dimensions left, so I can draw it vertically. Or maybe you could sit on the rope. You could even sit on the rope. So you could sit on the rope or you could push on the rope, but basically, if you apply the biggest force you can in the middle of the rope makes a really small angle. So then the perpendicular force that you apply is multiplied by a big factor. That big factor is the reciprocal of the tangent of this tiny angle. So then the tension in the rope then pulls on your car and might get your car out of the snow. I've never tried it. I look forward to trying it sometime. So this is a little bit tricky because you have to think, well, what happens when the person stands on this cable and it stretches? So it stretches out into a kind of triangular shape like this. And then by symmetry, the tension on this side is the same as the tension on this side since the person is standing in the middle. That may or may not be true if the person is not standing in the middle. Then we can do the force equations for equilibrium for this little dot. So we had the weight down and we had the vertical component of the tension up for both sides here. So that gave us 2t sine theta up and it gave us mg down. And then instead of theta being given, we were told this vertical displacement. So you know this vertical displacement divided by this horizontal distance, which is halfway across, must be the tangent of this angle. And then we did another tricky thing. We said, well, since this displacement is so much smaller than this length, for this particular triangle, the angle theta is so small that the adjacent is not very different from the hypotenuse. So in that case, the tangent is not very different from the sine. That's true for very small angles. We have two more questions here to answer. Is it possible to increase the tension in the wire so that there is no sag at all? In other words, make the tension so big that D is zero. I claim the answer is no, because it is the fact that D is non-zero which allows us to have a vertical component of this force created by the tension, and that vertical component is what offsets the weight. So if there were no sag, there would be no vertical component, and you need the vertical component of the tension, or maybe two copies of the vertical component of the tension, to balance the weight. So you see, if it didn't sag, it would have no way to balance the weight. Isn't that interesting? What happens to the tension as we make the sag smaller and smaller? Well, you see we have this sine theta downstairs. So as you make the sag smaller and smaller, sine theta gets smaller and smaller. Or alternatively, you could say, you see we have this d, the sag, in the denominator. As you make the sag smaller and smaller, but this weight stays constant, the tension gets larger and larger. So the smaller you make this sag, the larger and larger the tension has to be, so that the vertical component of the tension is enough to balance this weight. That's worth pondering for a minute too. I want to use this example we just worked out to make a little digression to talk about Hooke's law for elastic materials. This is another form of Hooke's law, different from, but related to, the Hooke's law for springs that we saw earlier in the course. So we initially had a 50-meter long wire going all the way from end to end, and we're told that that wire sags downward by D is 1.0 meter under a load of 500 newtons. 51 kilograms times 9.8 newtons per kilogram is 500 newtons. So each half of the wire was initially, I'll call it little L0. That's half of big L0. That's 25 meters long. And then each half stretches to, I'm going to call it little l, is the square root of little l initial squared plus d squared. That's 25.020 meters. So each half stretches from 25.0 meters to 25.020 meters. So each half of the wire stretches by 2 centimeters in length. So we're going to define strain. To be more precise, you might say axial strain or normal strain, to distinguish it from something we'll see later, which is called shear strain. But in any case, for now we can call it strain. So strain, and we'll usually use a lowercase e for strain, and that is the change in length divided by the original length. So L minus L initial divided by L initial. So in this particular case, that strain is 0.020 meter divided by 25.0 meter. So that's the change in length. 25.020 minus 25.0 is 0.020. And then in the denominator, you just have the initial length. So that's a pretty small fraction. You work it out on your calculator. It's 8.0 times 10 to the minus 5. And notice that it is unitless because it's meters divided by meters. Change in length divided by length is just a fraction. It has no dimensions. Next, we define stress. And for that, we usually use lowercase f. And that is force per unit area. Now, Hooke's law for elastic materials says that the stress is the elastic modulus times the strain. And there are different types of elastic moduli, actually. So to be precise, we call this one Young's modulus. So stress equals Young's modulus times strain. The units of stress are newtons per square meter, force per unit area. The units of strain are dimensionless. So to make the units work out the same on both sides, the units for Young's modulus must be newtons per square meter. It turns out another name for Newton per square meter is Pascal. I say this only because you'll see this in tables sometimes. So PA is the abbreviation with a capital P, and it's called a Pascal. If you write it out as a word, it's lowercase p. So Pascal is another word for Newton per square meter that you might encounter if you see atmospheric pressure, or if you look up a Young's modulus, or if you are calculating stress. Now, in the high wire problem that we just solved, we found that the tension in the cable was T equals mg, the weight of the person, divided by 2 sine theta, this small angle between the horizontal and the deflected orientation of the string. And if you plug in numbers, that works out to be 6,250 newtons. So we know the force, it's just the tension in the cable. So if we knew the cross-sectional area of the cable, then we could work out the stress. It would just be the tension divided by the cross-sectional area, pi r squared, of the wire that the high wire walker is standing on. So we know the force and we know the strain. So if I told you the Young's modulus of the material, then the only unknown we would have is the radius of the wire, and we could solve for that. We could figure out how thick a wire you need for this problem to make sense. If I tell you that the wire is made of steel, then steel has an elastic modulus of 2 times 10 to the 11th newtons per square meter. When I looked that up, it was listed as 200 gigapascals. Giga means 10 to the 9th, and Pascal means Newton per square meter. So 200 gigapascals means 2 times 10 to the 11th newtons per square meter. And by the way, if you look up elastic moduli in US customary units, you'll see numbers quoted in pounds per square inch. So for a wire of radius r, whose tension is known, we calculated it, we can write down the stress equals Young's modulus times the strain. And this stress is force per unit area. So the force is the tension that we solved for. The area is just pi r squared for the cross-section of the wire, the cable that the high wire artist is standing on. We know the strain. We know Young's modulus. We calculated the tension. So we can solve for r, figure out how big a wire we need. And then if we plug in numbers, we get a radius of about 1 centimeter. So a diameter of about 2 centimeters, a little less than an inch. So that's a pretty thick cable that we would need to support this 51 kilogram person, such that a 50-meter long end-to-end cable only sags by 1 meter when she stands on it. So that's sort of interesting. You look at the scenario for this problem we solved a moment ago and you say, is it realistic? It's kind of marginally realistic because a cable that's like almost an inch thick is a pretty thick cable, but it's like right on the edge of being realistic. Now, I called this relationship Hooke's law, but that seems a little mysterious to you because earlier in the course we introduced that Hooke's law was some spring constant times the change in length of a spring. So F equals K times the change in length seems different from F equals Young's modulus times strain, and even the F is different. This is force per unit area instead of force. It turns out we can relate these two to one another. Suppose we have a wire suspended from the ceiling, and its length is L0. Then we take another copy of that same wire, and we apply a force to it by hanging some known weight from the end. Then there's going to be some force mg exerted by Earth on this little object here. So then to keep this object in equilibrium, the wire will stretch out, its length will increase. As it stretches out more and more, the force that it exerts on this little block increases. Eventually, the force exerted by the wire on the little block equals the force exerted by Earth on the little block, and the little block is in equilibrium. So the wire reaches some new length L. And we'll assume this is a wire that has a cross-sectional area A. So we can work out the stress and the strain. So the strain is L minus L relaxed divided by L relaxed. So we call that lowercase e. And the stress is the force per unit area. The force is the tension, which also equals mg for this block that we put on the string. But in any case, Hooke's law tells us that stress equals Young's modulus times strain. So now we can solve for this force, and we get Young's modulus times the strain times the cross-sectional area of the wire. And the strain is just a change in length divided by the unstretched length. And now this is starting to look like Hooke's law. All we have to do is separate out this one factor. So it seems as if we could call this quantity Young's modulus times cross-sectional area divided by length. We could call that the spring constant. So that's pretty interesting. It seems as if we just take a piece of metal or some other elastic material and just use a chunk of that material as a spring, then the spring constant is proportional to Young's modulus. I guess that means if we use a stiff material like steel, we'll get a stiffer spring. If we use a less stiff material like rubber, we'll get a less stiff spring. The spring constant is proportional to the cross-sectional area. So if we use a 1 centimeter thick steel wire, we'll get a stiffer spring than if we use a 1 millimeter thick steel wire. And it's inversely proportional, the spring constant is inversely proportional to the length of this chunk of material. That's a little surprising at first. That means if we take a half-meter long piece of wire, it will be stiffer than a 1 meter long piece of that same wire. Let's see if we can see that happen with ordinary familiar springs. Here's an ordinary spring that you might see in any physics classroom. Here's 2 more copies of the same thing. I'm going to take this first spring and put it at kind of ceiling height, and then I'll put a half kilogram mass on it. Let's see how far it stretches. Okay, you can make a note of that. Now let's take all 3 of the same springs, connect them end to end, and see how far the bottom stretches when I put that same weight on the end. Oh, it clearly stretches quite a bit more. And if my model is correct, that second stretch should be 3 times as big as the initial stretch. So it turns out if you put 2 identical copies of the same ordinary Hooke's law spring in series, the spring constant is 1/2 of the original spring constant. And if you put 3 identical ordinary Hooke's law springs, one after the other, end to end, then the resulting spring constant is 1/3 of the spring constant of each spring all by itself. That kind of makes sense. That's like making a longer spring, and you see this length is in the denominator. And then another thing we'll see at some point is if you take 2 ordinary Hooke's law springs and you stick them side by side, then the resulting spring constant, if the springs are identical, is twice the spring constant of one spring by itself. And that also sort of makes sense because if you take these 2 pieces of material and put them side by side, their cross-sectional areas are adding up. Like the cross-sectional area of the 2 things side by side is just the sum of the 2 cross-sectional areas. So it turns out if you put 2 springs side by side, their spring constants add. As a digression to this digression, if you take 2 springs and put them end to end, then the reciprocals of their spring constants add. So the reciprocal of the combined spring constant is the sum of the reciprocals of the individual spring constants. I'm not even going to write that down because the main point I wanted to talk to you about here is simply Hooke's law for elastic materials. Stress equals Young's modulus times strain. Strain is change in length divided by original length. Stress is force per unit area. I usually write lowercase f for stress, which is kind of like a diminished form of uppercase F for force. And I usually write lowercase e for strain. Some textbooks use something that looks more like epsilon for strain. So depending on the context, we might say Hooke's law to mean little f is big E times little e. Stress equals Young's modulus times strain. Or, as in much earlier in the course, we might say Hooke's law is force equals spring constant times change in length of an ordinary laboratory spring. Now, not only do you know this second definition of Hooke's law, which will be ubiquitous if you study architectural structures, you also now know that the version of Hooke's law that you learned earlier in the course can basically be derived from this materials form of Hooke's law. Okay, end of digression. Now here is a similar problem without the mirror symmetry. Now suppose a 51 kilogram sign is suspended from a cable, but not at the center, as shown below. How would you find the tensions T1 and T2? Once you know T1 and T2, what are the horizontal and vertical forces exerted by the 2 supports on the cable? We are slowly segueing into the idea of a truss. So this cable number 1 is at an angle 26.6 degrees with respect to the horizontal. Cable number 2 is at an angle 14.0 degrees with respect to the horizontal. Where do we come up with such crazy numbers? Well, I think this 14 degrees must just turn out to be the arctan of 1/4, the arctan of a half meter over 2 meters. And this 26.6 degrees must just turn out to be the arctan of 1/2, the arctan of a half meter over 1 meter. So really, this vertical distance of a half meter and these 2 horizontal distances of 1 meter and 2 meters were given. And I worked out the angles that corresponds to by taking the arctan. Yeah, so this 14 degrees is just arctan of 1/4, and this 26.6 degrees is just arctan of a half, if you're wondering where they came from. Here is our 51 kilogram sign. How do you find the tensions T1 and T2? Well, it turns out we can just take this hypothetical point P and say it must be at equilibrium. And we have horizontal and vertical force equations we can write at point P. Is there a torque equation we can write? No, it actually turns out there is no torque equation we can write for point P because all 3 forces have lines of action that pass through the point P. All these forces pass through this same point, so there's no torque equation we can write. But we can write a horizontal force equation and we can write a vertical force equation, and we only have 2 unknowns. Good thing we only have 2 unknowns because we only have 2 equations to find these 2 unknowns. So here we go. So the horizontal sum of forces at P is 0. That tells you right minus left, T2 cosine theta 2 minus T1 cosine theta 1 equals 0. So if you know one of them, you can get the other one this way. The other equation is the sum of the forces in Y at point P is 0. That is, let's do up minus down, T1 sine theta 1 plus T2 sine theta 2 minus big M G equals 0. So that's all you need. You have 2 equations and 2 unknowns, so we can solve for T1 and T2. It's a little bit tedious to do so, but you can do it. Then, once you know T1 and T2, we can actually figure out the horizontal and vertical forces exerted by the 2 supports on the cable. So at A must exert FAX equals minus T1 cosine theta 1. So it has to be, A1 must be pulling to the left since T1 is pulling to the right on A. And then there's FAY equals, well, I'd say that's, see, so this is to the left, this is up. Well, if I draw the arrow that way, this becomes a plus sign. So if I say the x component, then it would be to the right. But if I actually explicitly label it, this is AX, and I draw it to the left, and this is AY, and I draw it up. Well, if I drew AX pointing to the left, then I'm asking for the part that points left. So that's then plus T1 cosine theta 1. And this is T1 sine theta 1. And then at point B, B must exert FBX. So let's say we're going to draw BX this way and BY this way. So B must exert FBX equals T2 cosine theta 2, and FBY is T2 sine theta 2. So we're really really only two unknowns in this whole problem because we are told these two angles, basically. Well, we're actually told this height and this width and this width and this height, but that's equivalent to being told these two angles. In this last case, writing down the equations was much more interesting than actually solving them. And the trick that we used here was to put this point P at equilibrium. And doing that requires us to write that the sum of all the forces in X acting on this point P, forces to the right minus forces to the left, and then for all the forces in Y acting on this point P. So these two forces up minus this force down equals 0. So we had T2 cosine theta 2 minus T1 cosine theta 1 equals 0. And then we had T1 sine theta 1 plus T2 sine theta 2 minus this weight equals 0. This turns out to be exactly the method we will use to analyze a truss by a method called the method of joints. And we will start doing that pretty soon, within the next couple of lectures. But meanwhile, that's all I have on chapter 12 about torque. So I'll see you in class.